shortcuts. And which shortcut you use does depend on what type of function you're given to start with. Okay, so and some shortcuts work for various ones. We're going to go with the simplest shortcut today. It's pretty much called the power rule. A lot of textbooks, though, give a separate constant rule. Not really sure why they do that, because they don't have to. Because I still think it falls under the power rule. It's the same shortcut, really. It says here that if you had to calculate f prime of x in example 1, and the function you were given was 3. Well, let's think about that for a second. That basically means y equals 3. Are you in agreement with that? So it's really that equation. So what's the slope of the tangent line anywhere I pick it? 0 is the slope of the tangent line, correct? No matter where I pick it on that line, because the tangent line is just going to keep doing that, right? And so the derivative of this, of any constant function, so you see why they call it a constant function? Because all you have in there is a constant. There's no variable. They say that the derivative of that is 0, which we can plainly see over here. Okay. But again, hopefully you can see, or maybe you can help me figure out why I really think it's just the power rule. Now, this only works if you have just one, like a monomial. You agree 3x squared is a monomial, just one term. Not one term multiplied by another one, or added to another one. It's just one term, correct? Find the derivative is quite simple. And remember, if we did this by the definition, here's what we'd be doing. The limit as delta x goes to 0 and all that stuff, right? Okay, well, here is the power rule. Are you ready? Take your exponent. Multiply it by the coefficient, which is 6. Write down the variable. And take the exponent down a power. Done. That's one of the shortcuts. That's the derivative. Okay. So it's the derivative is, in other words, just 6x. So again, that would have taken us a few minutes, maybe doing it the other way, just cleaning up all the stuff, but we should have still gotten 6x. Okay. So how can somebody explain to me why I gave the suggestion that the same thing really works for that one? Any ideas? Yes. Because I still think, yeah, exactly. It's really 3x to the 0 power is 1. Whoa, that's not a 0, right? Do you agree that x to the 0 power is just 1, right? So could I rewrite 3 as 3x to the 0? Yeah. So then you go 0 times 3 is 0 times, well, who cares what it is? It's 0 times something, so it's 0, all right? So it's really just the power rule. So now here, remember how hard 1 over x was? Remember doing that one? It took forever, right? You know, we had to get the common denominator and all that stuff with the definition. Well, we can still use the shortcut, believe it or not, but right now, the variable's in the denominator. I'd really rather it wasn't there. I'd rather be able to do it kind of the way I did the last problem. So is there any suggestions on how I could rewrite this function so that it's a little easier to take its derivative? Yes? Exactly. X to the negative third power is exactly the same thing as 1 over x to the third, correct? Okay. So here's where that chapter 5 in Algebra 2 comes in handy when you get to start rewriting things, because now this derivative just got really easy. Okay, this is not the only way to do this problem. There is another shortcut that would take care of this problem, but it's much more complex than this. So here we go. What's the coefficient really out front, though? A 1, right? So the exponent's negative 3, which you take times 1, which is negative 3. X, now you have to be careful. What did I say to do? Take the exponent and go down a power. So what would be down a power? Negative 4, correct? Down, right? Or further left on the number line, I guess you could say, right? And so what I would do is probably clean it up. So of this, the negative 3 is really still in the numerator. Because what's the exponent on negative 3? What's really the exponent on that? It's really a positive 1, right, on that one? And so then it's x to the negative 4, which would really rather be down there, right, if we clean it up. And so there's your derivative. Well, that took substantially less time than 1 over x did the other day. Okay. Any questions on that? Because again, let's just do 1 over x real quick, and maybe we remember the answer. We could rewrite it as x to the negative 1, right? So it's negative 1, x to the negative 2, or negative 1 over x squared, which is the answer we got the other day. Whoa, did I miss a page or no? Okay, sum and difference rules. Basically, it's saying if you're adding and subtracting monomials like that, you can just take each piece separately. If you're adding or subtracting, notice did I say anything about multiplying and dividing pieces? No, I did not. Okay, so if you start multiplying variables together or dividing them, this shortcut's not going to work, which is why we have to have other ones. Okay, but this shortcut works really nice right now. You can just take it piece by piece. So f prime of x. So here's x to the fourth. What's the derivative of x to the fourth? 4x to the third, right? How about this next term? You just take, because it's just adding and subtracting it, and it's just got one variable, so negative 6x, right? And the derivative of 7 is 0, right? Because it's 7x to the 0, right? And so the derivative of that is 0. There it is. Well, if you don't like the shortcuts, there's no rule that says you have to use them. You can always do them by hand. So what about example 5? Sometimes people get a little scared when they see this. Well, it might help to rewrite it a little bit. So negative 3/5 x to the third is the same thing, right? I would say plus 3 pi x to the negative 2 minus 2x, right? That's really the same thing as what was written before. Now, the reason I chose to write it that way is I think it's easier to see how to use the power rule on this. Notice, is there any prime on what I just wrote? Is this f prime of x? No, it's just f of x, which means I just rewrote it, right? So now we're going to go and do f prime. Okay, everybody ready? So we've got this negative 3/5, and then as the coefficient, and this 3 is the exponent, correct? So if we multiply that, that's negative 9/5, right? X to the second, very good. Oh, wait a minute, I said if we have variables multiplied, you can't do this. I got like a 3 pi here. It's not a variable exactly. That's just some irrational number, right? 6 point something, right? 6.28, blah, 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 right? So that's really just a number. It's just a coefficient written differently. So let's go, really, let's take this 3 pi, and then times negative 2 is negative 6 pi, right? Now careful, x to the negative third, very good. How about negative 2x? Really negative 2x to the first, right? And so it becomes negative 2x to the 0. Agreed? We take it down a power? Everybody with me so far? So now we can just kind of clean things up a little bit. Negative 9/5 x squared. I don't really have a problem with that. We should probably clean this one up, though. So it's minus 6 pi over x to the third. And then minus, well, it's really negative 2 times, what is x to the 0? Just 1, right? So it's negative 2 times 1, which is negative 2. So you can just imagine how much fun that one would have been with a pi with delta x doing the definition. Would have been wonderful fun. That's right. More fun than you can handle. You got it. All right. Does the function blank have any horizontal tangents? Whoa. If yes, where? Huh. Well, we could graph it, right? You with me on that? We could do that. And in fact, maybe we should get the graphic calculators, but we'll do that in a bit. But right now, how could we do this otherwise? How could we do it algebraically or basically via calculus? Oh, find the derivative, I've been told. Okay, we can do that. So now if it's starting with a y, so normally the notation would just be y prime is one you can use. Or if you like dy dx, you can use that one. Equals, well, let's find that derivative, and we've got what? 4x to the third minus 4x. What do you do with that plus 2 again? Yeah, it just goes to 0, right? So that is our derivative. Are we in agreement with that? Yes, no, maybe? Now, I was told by someone here that we should set the derivative equal to 0. Why would we do that? Right. Basically, if we're looking for something that's horizontal, if I want my tangent line, that's not really very horizontal, but if I want it to be horizontal like that, what's the slope of it? 0. And where do you put what you want for slope? You put what you want for slope right there, because that's what the derivative stands for. And I want to know what x value it happens at. So could I ask you right now, find where the slope would be 7? Yeah, then where y prime is, you would put 7, Okay, but I'm just asking for horizontal, which means it better be 0. So let's set it equal to 0. And then algebraically, we would need to solve that. Okay. Any suggestions on solving? Yes? I would leave the 4x where it is, actually. Yeah, I would factor. There's a 4 in common and an x in common. Once I do that, it's x squared minus 1. The reason, again, this works, remember, is this is 4x times something else. So one of these other has to be 0 for it to actually end up being 0, right? So what I would do is set each one of these equal to 0. Because either this piece or that piece has to say 0 for this to work, because 0 times anything is 0. And so what makes 4x equal 0 is if x is 0. Ooh, that's a good one. And then over here, you could do a difference of 2 squares on that if you wanted to, right? Or couldn't I just add the 1 over and take the square root? You with me on that? I got some people looking. Everybody good? Okay. So let's just add the 1 over. So x squared equals 1, square root, housify. So x equals, careful. Very good, positive and negative 1, because we introduced the square root in part of our solving techniques. So apparently, this will have horizontal tangents in 3 locations. Okay, so I'm going to write this down over on the other board so I can bring up the graphing calculator. And we got x to the 4th minus 2x plus 2. Oh, did I miss one? What did I put? Oh, yep. Thank you. It's 2x squared. So what was it? X, positive 1, negative 1, and 0. So let's go to where x is negative 1. I believe that's that point right there, correct? You believe that's a horizontal tangent? I do. And what was another one? 0, that's where the point is, horizontal tangent. Horizontal tangent. Okay. There they are. Whether you graph it or not is completely up to you. If you understand horizontal tangents, then you need to decide if you need to graph it or not. Okay. I'd say it's not a bad idea to know kind of what it would look like where there's horizontal tangents. Okay. But again, I could have asked you for any particular slope here, and you could have found the x values that would have made that happen. Okay, I think that was it, right?
Yes.
That's the last one. Okay.